Hello, I'm Kris, and welcome to Law of Demeter, a practical guide to loose coupling, in which we'll be talking about how to not break the law on a daily basis. So hopefully you'll enjoy that one. It's a practical talk, so there will be a lot of examples of code in which we'll take a look into what is a good practice, what is a bad practice. So keep that in mind. I hope that sounds exciting because it will be hopefully for you as well. So what we'll be talking about, we'll start from the motivation, why we actually care about loose coupling, why we care about the law. We'll define the loose coupling and take a look into what to do in order to not to have it. We'll take a look into law of the matter. We'll define it and take a look into how we can fix it. And we'll take a look into some of the solid principles in order to do so. One of them will be single responsibility. We won't talk about others until we'll talk about dependency, inversion, and injection, which will help us understanding the whole loose coupling. And we'll sum it up with potential, maybe learnings out of this talk, hopefully. There will be slides which will have dark blue background, and they are really important to remember. There will be a lot of slides. Some of them are less important than the others, but the dark blue ones are, in my opinion, the most important ones which are worth remembering, if anything out of the talk. So what's the motivation? When you read Uncle Bob, you know the only way to go fast is to go well, meaning that without having a good quality code, we won't be able to go fast in the long term. It's feasible for a short term, but not for the long term. So that's my two favorite books about loose coupling and basically software design. If you haven't read them, I really encourage you. The Clean Code, obviously, all the solid principles from Uncle Bob. And the other one is The Pragmatic Programmer. I think it's my favorite book ever, with a very good practical knowledge about how to approach software design. And out of this book, there is this, for me, the most important quote, which I'll share with you if you haven't read it, the essence of good design. And that will be going through all this talk, because everything in the end just comes to that. And what is that? A good design is easier to change than the bad design. That's the most important lesson out of this talk. Yeah, you have it, 5 minutes in the talk. But why is so important? Because all the rules which we know about the solid principles and all the laws, law of matter, they come just to this one thing. Because why? Solid principle, single responsibility. If you separate concerns, it's much easier to change them in separation, right? Meaning the design is easier to change. Good naming. Code is much more often read than written. If you have good naming, it's easier to change, right? What about law of the matter? If you have something which is loosely coupled, it's much easier to change. And you can apply this rule to everything which we have in the good software design. And that's what we'll be going through the talk. It's called ETC as well, the shortcut. So keep that in mind, and please remember that slide. And I would encourage everyone to just go through, whenever you design something and try to write the code, the first thing about the essence of good design, meaning, will that code will be easier to change in the future, or it will be harder? It's not always easy to know that upfront, but sometimes we know. Sometimes we can apply the techniques upfront, which will get us there. Sometimes we'll make a mistake and we'll have to pay for that in the future. But it's really good design to have in mind. To be more specific, there are a few other things which we will take a look into today. Design has to be also flexible, meaning that there is nothing, there's a Franklin rule, which says there is nothing certain in software development except of bugs and constantly changing requirements. So we have to have a flexible design. We have to be scalable, meaning design have to be easy to extend, maintain, and reuse. And please think scale, right? We don't want to talk about a very simple main function which has hundreds of lines of code. That doesn't matter. We care about really large, huge project. Think Google scale, for example, or maybe a bit lower, like 200 million lines of code, 1 million lines of code, 100,000 million lines of code. 100,000 lines of code, sorry. The design has to be testable. Because if you don't test our software, users will. And users, stakeholders, might be anyone. Might be yourself, if you write the code for yourself, or anyone else. But there is always stakeholders which are on the line. And if we don't test and we don't trust our software, they'll definitely figure it out what's wrong with it. And obviously, I always follow the rule, the Beyoncé rule. If you like it, then you should have put a test on it. If you didn't like it, you shouldn't write it in the first place, I guess. So I hope the motivation sounds good. So let's take a look into loose coupling. Loose coupling meaning easier to change code, right? And we'll take a look into examples of what's good and what's bad and how to approach it. So let's start from something very simple. Keep it simple. You know the rule. Keep it simple, stupid. Stupid, all right. So let's assume we have a CppCon talk. The first thing we notice here, it will be the premature optimization, because we'll put the attribute always inline, because that's the rule in our company, that everything is always inline, because it's faster, right? We never measured, but it's always inline. Sounds better than never inline, right? It will be faster. So premature optimization is not the best way to go up front without measuring. After that, we'll have the speaker. We'll obviously get it. I don't know whether anyone has seen code like that? Everyone, just for the audience, recording everyone, raise their hands. Thank you for that. So here, what's the issue? We have the manager. What's the manager? What's the responsibility of manager? Why we have it? What's the name? Let's say it's in descriptive naming in general, because it's a manager, right? It's a God object which is responsible for everything. After that, we have this instance, meaning that it's a singleton as well. That's even better, right? Because we won't be able to test it at all, because how to fake singletons? We have a global variable in the code. Not great. So that's untestability as well. And after that, we'll get the get speakers, dot get, dot get, dot, dot. Notice that we chain a lot of things here with dots. And what's bad about it? Well, we'll take a look, because that's related to the law of Demeter. But also notice that the speaker, which is unfortunately me for you guys and girls, is the fact that it's coupled. It's set in stone, and we cannot change it here. Also, we have attendees, and notice that we will get the same pattern. From the manager, we'll get the instance, we'll get attendees, we'll get the underlying attendees, which are coupled as well. And then the speaker will talk, and attendees will ask questions in the end. So all of that is not really a good design. Why? Because it's not easy to change, etc. As I pointed out before, there will be a lot of that. Why it's not easy to change? Is it flexible? Well, not really. It's tightly coupled, right? We cannot change the speaker if you want. You're coupled to me. I'm coupled to you. Is it scalable? Not really. It's hard to extend. If you want to add new functionality, it will be hard to add it because of the coupling. Is it testable? Well, definitely not easily testable, because we have to how to fake singletons. It's really difficult, and it's really difficult to fake all the chain of commands, because when we have get and get and get and get, we have to fake all the layers in order to fake the last thing. So all of that is not good. So what are the problems? And you will see the pattern here where I'm going with it. Singleton, that's bad. Tight coupling, that's bad. That's bad too. Untestability, not great either. Premature optimization, as pointed out, not great. Indescriptive naming, also not great. Well, and any ideas what will be here? Duplication. So we ended up with not the great code, to say at least. But there is more problems with that. And the main problem is the fact that we're breaking the law here by having this dot, 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 dot thing, because it's really hard to fake that. It's really hard to reason about it. It's really hard to see what's the problem, how this design can be evolved. It's really hard to extend God objects. As I pointed out, this rule, this dot, 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 is breaking the law. And the law of the matter, which we don't want to break because it's tightly coupled. It couples us to the design. It couples us to everything. And the law, it says, it's very simple. It says only talk to immediate friends, meaning from code perspective, just have one dot. One dot is enough. Inject everything. Inject the objects which have only one dot, which you can access elements you want out of them. Don't chain a lot of things. And the exception here is, for example, ranges, right? When you pipe a lot of things. Instead of the dot, you use pipe in C++. That's an exception, but by default, you don't want to chain. In pragmatic programmer, they say don't chain method calls. And that's what we don't want to do. Don't want to have these get speakers, get, because that's really difficult to test, really difficult to reason about, and it's really tightly coupled. So what's so bad about it? It's tightly coupled, it's almost impossible to test, and really hard to extend, as we pointed out. So how to fix it? That's the main part of the talk which we really want to focus on. How to fix it? Well, let's see what it's not a fix. Well, changing C++, right? I said that the law of the meta is about dots, and that's what you see about Java and other languages. What about C++? Well, we know exactly what to do, right? We change references to pointers. And we're good, right? We have, how many dots? How many dots we have? 0. So it's even better than law of the matter, right? Because they said you should have 1. We have 0. We inject everything which is required. No. So that's not a go. Because it's, a lot of, C++ community is really smart. So you have to say that up front. What about that? How many dots we have? Well, per line is 1 dot. So are we good? Well, not really, because it's the same issue, right? We still have manager instance, which is a singleton. We still have speakers, which are accessed through the instance, and then we have the get as well. So that's also not a good idea, and that's also not fixing the problem. That's like fixing a problem by avoiding it. So that's not good. The proper way of fixing it, in my opinion, is by applying solid principles from the clean code, the proper way, because we will take a look into how to apply, law of the matter might be applied, like how to fix it, right? How to fix it might be done this way. It's the same with solid principles. All of them might be applied sort of, I'm smarter than you are kind of way, and, you don't want to outsmart like Uncle Bob with that. And in my opinion, the best way to fix it is by applying test-driven development or behavior-driven development. We'll take a look into that, because what they give us, a testable design by default is easy to change because it's testable. And if you started from writing a test, you'll write a design which will be testable. And if you can change the test, you can change the design. So etc, easy to change. Applying solid principles also will give us to etc, but a bit longer way, in my opinion. So I hope that makes sense. But yeah, let's take a look into this solid versus stupid, which I hinted at before. So when we think about the solid part of it, it's the solid principles from the clean code, and they are like solely single responsibility, open close principle, risk of substitution, interface segregation, and dependency inversion. We'll talk about the single responsibility and dependency inversion here, and they are really all of them are related to fixing the loosely coupled issue, but they are the main which I will focus on today, and I think they are the most important part. Obviously, we've taken a look into the stupid part of it, where having a singletons, tightly coupled code, not testable code, premature optimizations, bad naming, and duplications will never give us a really good design in the end, and will be hard to change, meaning we won't be applying to etc. So let's try to fix it. Single responsibility principle will be the first approach we'll take. And what is single responsibility principle about? Just because we can do a lot of things in one place doesn't mean we should. And single responsibility is like Swiss knife, where you have everything in one place, and that's bad. So single responsibility principle is just about having one thing. A class should have only one reason to change, not multiple. And if you have multiple things, meaning the design is harder to change because we have multiple things to fake, multiple things to change. So how that would look like, but it's really important also to understand that single responsibility principle doesn't mean that the code won't be coupled. It will be better, but it still might be coupled. So for example, if you have the speaker here, the name is coupled to the code, but we have a speaker class which is single responsibility. There's just speaker is talking. There's no other responsibility here. Give a talk, but the talk is given by a specific person which is coupled. It's the same with the attendees. The responsibility is to ask questions. However, we tightly couple the names, which also, it's not great. How about, the talk itself? So when we have this object, it's already better than before, right? Because we don't have manager instance get. We have our objects here, meaning the design is easier to change because we separate the concerns. We can easily test speaker and attendees in separation. Although they're still coupled, we can still test them. CppCon talk, it will be harder to test still, but it's much better than it was, in my opinion, because it's easier to change. Easier to change the speaker, easier to change the attendees. So we head in the right direction. And we also don't have always inline anymore, meaning faster already. So what about this flexible design? It is better because we separate the concerns. We have the speaker and the attendees class. So it's better than it was. Is it scalable? A bit easier to change because we have these classes, additional single responsibility classes. But all in all, it's still coupled. So it will be hard. Is it testable? I would argue it's hard to test because, for example, attendees and the speaker they're coupled to the names. So it's really hard to fake that part if we say about it. But it's easier because we have the separation. So what's the learning here? Because etc is better in that regard, I think we should consider classes to have only one reason to change, meaning we should apply single responsibility principle when possible. But not necessarily, we should go further. We shouldn't stop there. So etc, out of this part, we just here. Let's go further then. So, dependency injection is a scary term. It's like, I gave the talk once when, it was called $25 term for 25 cents concept and term, and that's what it is basically about. Dependency injection sounds scary, but it's really simple. What is it about? Dependency injection. Dependency injection is about a way to reduce coupling, meaning, this talk is all about coupling. Like Law of Demeter is about coupling. We have multiple dots, which we try to avoid. How we avoid them? By lowering the dots by injecting things which we really require. And that's the reduction of coupling. The best way of doing it in C++ in principle, I guess, for the dependency injection is just via constructors. You can do it many different ways. You can have methods which initialize or other ways of doing it. But the most constructive way, in my opinion, is to use constructors. But whether DI can be totally misused, and we'll take a look into examples how that can be achieved. But basically, in principle, whether DI is done right or wrong depends on what we pass into those constructors. And very important thing, DI doesn't imply using a library or framework. Although there are good ones, I wrote one. I think it's a good good usage of developer time in a scale. So when we have it's like I wouldn't apply DI framework for a code for a small project, but for the big project, when we, don't want to spend most of the time dealing with the wiring and creating objects and passing them through, DI framework is something which I personally believe is very handy, and it has benefits. But also it has also drawbacks because we have to learn something and we have to apply it consistently. And one thing which is really important also regarding the DI frameworks is we don't ever want to couple ourselves to the framework itself. So in C++ it's hard to get the reflection out of a constructor, but you can do it. And if you have to put a macro or change, parameters to only be shared pointers or only references or only pointers, you don't want to do that, because when you couple yourself to the DI framework, which is the main reason why you don't want to, why you started to decoupling yourselves from it in the first place, right? And right now, you reduce the coupling by introducing new coupling. Not great. So let's take a look into DI versus not DI. Tightly coupled speaker, as we pointed out, nothing specific here. As we had this example before, speakers and attendees are coupled. So the simple solution here for the speaker will be, well, I'll just inject the name. Voila, we have dependency injection, we inject the name. There's like nothing more about dependency injection than that. What we inject and how we inject that, that's a different story. That's really important to understand that we can screw that up. But in principle, dependency injection is just about injecting things into other things. And we can inject them many different ways, right? We can inject it via templates, via constructor, via interfaces. There's many different ways of doing that. But the main principal idea is we inject things. And how the talk itself looks like, we inject the speaker and attendees. We don't inject names here or anything else. We inject these objects which are required for this given class. And this way, notice that we will be able to achieve Law of Demeter because we'll just have one dot. Because speaker will have dot talk and attendees will have dot ask. If we inject something else, which we'll take a look into, we wouldn't get that. So I hope that makes sense. DI is often called as a Hollywood principle, which means don't call us, we will call you. We call, when we try to use the manager instance get, we call them. And We want to be called. We don't want to call, in a sense. But there are gotchas. With DI itself trying to fix everything with the coupling, we can screw that very easily. For example, by not using constructors consistently. So imagine that we have the speaker takes the name, right? Great, but then we have a CppCon talk in which we hardcode the name for the speaker. So yeah, from the speaker perspective, we can easily unit test that, and it's awesome. But from the CppCon perspective, well, we tightly coupled ourselves again. So that's not great. So the rule here is to use it consistently. So that's bad, but that's good. If you inject the speaker, that's always good. We can also use singletons, because why not, right? We can have the speaker instance get talk. That's bad. That's really bad always, meaning that we didn't apply the DI at all, actually. Getting it from the singleton is not ideal. However, for the DI perspective, it is possible to use still singletons. If you really care about having one instance, instead of, the speaker might be injected from a singleton perspective, right? So we have a CppCon talk, and the speaker, it's still being injected, but where it's coming from, it might be coming from a singleton class. And then we just inject that object. But we don't access this object from within the code, the business logic. We don't want to, make the concerns about business logic and object creation together. That should be separated. The creation is part of the factories, DI, and object creation. And then the business logic is where the algorithm lives. That's where developers make the money, not in the creation part. Creation part is boring and should be automated. And it can be automated by DI frameworks, for example. What about carrying dependencies? That's a very common mistake with DI, which means that we'll get the leaky abstractions because we have a speaker which takes the name, but instead of passing the speaker into the talk, we pass the name into the talk, and then the speaker will be initialized with that name. That's a leaky abstraction, which means that the design is not easy to change. etc is violated here because the talk doesn't care about the name. Talk cares about the speaker and the attendees. It doesn't care about the name. And the name is being propagated to the speaker for no reason. Meaning that when we have to check the talk, we have to create this object with the name instead of the speaker. So that's something which I think is really important to remember, because that's very commonly misused application of the DI, that we don't pass the right things. And it's also visible. So passing the name is bad, but passing the speaker is good. So let's keep that in mind. We can also do that with the inheritance, which is not great either. Sorry. And that's very common with the CRTP pattern. You probably heard of static polymorphism, when we have the class which inherits from the other class. And then, in order to initialize it, we propagate from the top layer all the arguments to the inherited class with, and some of them will take some arguments, some of them will take the others, or the order is important. That design is not easy to change. We violated etc, and it will be hard for us in the future. So we don't want to do that. Instead of that, we want to prefer composition at the first place. We don't want to use inheritance, but I understand that CRTP is something which sometimes is important. But inherited speaker is worse, in my opinion, than the composition one. And also, if we propagate the constructor parameters through the layers, we'll never get a good design in the end. What about talking to your distant friends? I don't know whether that, well, I would hope that talking to a distant friend, makes you think about the meaning of the talk, because it's related to the law of the matter. So imagine that we will inject a manager, because obviously right now it's not really that bad naming because it's a talk manager, so its responsibility, it's less managerial, let's say. It's still a manager, right? And let's see that the speaker will, get the speakers from his manager, and after that we'll get Kris. So it's a bit less coupled, right? Because we've taken the Kris. You can imagine that we could pass the name through the constructor as well, and then we pass the manager and the name, and when we get manager, get speakers, get the name. Well, that violates the law of the matter, because we have multiple dots here, so we don't want to do that. Instead, what we should do, we should inject the speaker, and that would solve all our issues here, because right now, to fake the manager, we have to fake the get speakers, get, and for Kris, we'll have to fake it as well to get specific object, right? If we inject the speaker here, we just fake the speaker. There's nothing else here to deal with it. So let's consider talking only to our immediate friends in the code, not in real life, even with COVID. So getting the speakers, getting objects with ... is bad, but injecting it is good. Like, you notice that the second line is always good. And why is that good? Because that, makes etc possible, meaning easier to change code will be easier to change design with minimal number of dots, which is 1. And that's law of the matter, right? We coming back to this really important law, which is often violated without even knowing about it. What about other things which we considered hard to change, making the coupling also difficult? Imagine this weak API, in my opinion, that we have a speaker which has the first name and last name. And both of them are strings, because, the first name is a string, last name is a string. What's wrong about it? Well, the fact is that the first name and last name don't matter, because the names don't matter in C++, right? We can say std string last name, colon std string first name in our declaration of the function, and the definition might be totally the other way around. Doesn't matter. So that's an issue, because that will compile, okay, and that will compile okay as well, but that wasn't the intent. Intent was first name and the last name. I know in my case that might be arguable to distinguish, but in principle, that's weak API. And how to fix it? Well, the best, in my opinion, way to fix it will be by using the strong types. Strong types are really beneficial also for DI, because they allow to distinguish things when you're injecting them. But in principle, there'll be a type which, instead of the string, it will be a named string which has different types. Which means we can avoid the naming of it, naming of variables, right? Because we have a strong API. The first name space first name, or last name space last name doesn't matter. The name doesn't matter, because the type itself contains all the information which is required for us to have the strong API. And then, if you do speaker first name Kris, last name, that's okay. But if you screw the order, that won't compile, because there are different types. And that's great, because that's what we want. We want strong types. We want C++ and strong type language to tell us that we screwed up, not the runtime testing, which we probably haven't done either way in all cases. So I hope that makes sense, and I think that's important. So let's consider using the strong types for good design and etc. So speaker with the strings is bad. Speaker with the strong types is good. And notice that we don't have these names here. We don't have to have them, and that's good because in the declaration of the function we don't have to have them, right? Or in the doxygen. But if we use the strong types, it doesn't matter because the type itself gives us all the information which we need. So we made it somewhat easier to change by following the single responsibility principle, by applying law of Demeter with dependency injection. So all of that is fine. However, it's still tightly coupled, right? We still make it hard to extend. And in order to fix that, let's take a look into dependency inversion principle. So dependency inversion principle is, is an idea that, if you compare that to real life, like here, this example, we wouldn't solder a lamp directly to the electrical wiring in a wall, right? Would we? That doesn't make sense because that makes us hard to change, right? It's like if we put a socket in the wall and have the plug in it, we can plug different things. And that's what we want because nothing is certain in the software except the bugs and the fact that the requirements will change. So we know that our manager or product owner will come and will ask about something else. And everything depends on our design, whether we'll be able to apply it and change it easily or not. If we apply, dependency inversion principle, we probably will get much better results changing it than if it tightly coupled. So all in all, we should depend on abstractions, not on implementations. And I think that's really important to have the distinction for. And it's like we can make that many different ways. But if we depend just on concrete implementations, we'll never be able to easily switch anything in our design. Means that it'll be really hard to change. We'll violate etc. and we'll violate a good design in the end. So in order to do so, we'll try to apply dependency inversion principle as well. There are different ways of applying polymorphism in C++, as you probably know, because it's C++. One of the ways is inheritance. So that's basically related to abstract classes and virtual interfaces, which has pros and cons. The pros are that it's object-oriented, very well studied, and it's applied from different languages like Java and other object-oriented languages. However, it has its cons because it's coupling us to the inheritance itself. So our implementations have to inherit from something. They have to know this interface in order to be able to implement it. And that's bad. And also, if you ever seen Sean Parent talk, inheritance is the base class of evil, right? So we prefer composition when possible, but because of the virtual classes and virtual polymorphisms, we cannot get rid of that. So that's bad. And also, the interface has this virtual part of it which makes the performance arguably slower, depending on the compiler. The virtualization not always is possible. And all in all, it probably will cost us. Type erasure is something which is very popular these days in other languages, like Rust, has the traits. We can apply type erasure in C++. The perfect example we have already. For example, std function is a type-erased thing. Shared pointer of void is type-erased as well. So type erasure is already applied in C++. However, we don't have really easy support to, for example, what I would preferably really like is to come from concepts to type erasure, like in Rust, when we have concept definition of our requirements, syntax requirements, and then we have something which can apply this concept to get type erasure thing. And type erasure, by type erasure, I mean like it will have the pointers to the signature of the functions which we define by the requirement in the concept. I think that would be very powerful. That really works well in Rust and other languages, but unfortunately we don't have it. And it doesn't seem like we'll get it with the reflection either. Another thing is std variant and std_any. std_any is like completely erasing everything. It has the benefit of the fact that it's really easy applicable for testing, for example. If in our fakes and handlers, I would argue that any is good for that. Not in the production as much, because it has really huge performance impact on the code. Because the way it works, it stores the void pointer in a sense and type, and after that there is a dynamic dispatch in order to figure out the types. And we have to, when we try to get it, we have to know the type from there. std variant on the other hand, and also it's always on the heap because we cannot predict what it will be. std variant on the other hand, it's closed with the types, so it gives us, it's like smart kind of union of things. So we always store the max size of elements which are in the variant. And it's really easy to have that as a polymorphic thing. You can even imagine like if you, but the problem with it is the fact that it's closed, right? So in the production we have A, B, and C, but in testing we want to use fake. But what about A, B, and C, which we just put in the variant? We cannot do much about that, right? Because in the production we care about the performance, we don't care about the fake in it, and we don't want to, ever, in a sense, we don't want to do define private public or anything like that, right? And we don't want to change the type for the variant. So there are two options here. One, we inject, dependency injection, etc. We inject the types, right? If you inject via template, we can say what type it will be. And we don't want to inject on the side note here argument pack of things into the variant, because that it's a leaky abstraction again. What we want to inject is the variant itself with all the types. So in the production, we inject the variant of ABC, and in the testing, we inject the variant of ABC fake or just fake. In that case, we don't have the leaky abstraction, and if you want to change the variant to something else, we can. Otherwise, we won't be able to. So that's important to have in mind. Another way of injecting polymorphism is templates. Obviously, that's very common approach towards getting a better performance. However, templates are contagious, meaning it's really hard to break templates when we start using templates. If you have templates on the main function in the, when you create the main object, you probably will have templates till the end, and templates have to be propagated. And that's not great from design perspective either, because it's harder to change, right? Because we have to change the template everywhere. There are ways of dealing with it, but by default, it will be difficult. And templates do not give us one important thing: they do not constrain what we pass, right? So it means that when we get the error, we get the error from our code, library code, which users may have no idea about. That dot foo is not found. It's like, but I didn't care about dot foo. Like I just wanted to do dot bar, and dot foo was required apparently. So concepts will give us gave us the ability that upfront will say full and bar is required, and if you didn't pass a proper type, we won't get there. And there are other ways of dealing with polymorphisms. I just wanted to quickly summarize what we can do. We'll take a look into concepts because I think that's the best way of dealing with the polymorphism regarding all the things. I pointed that talk out, so I wanted to give a shout out to Sean. It's a really good talk. If you haven't seen it, I really encourage you to watch it. And regarding all these concepts, and while it's dealing with the type erasure and functional programming, like DI might be applied in the functional programming. All the concepts might be applied in functional programming as well. And I think it's really important to distinguish the fact that C++ doesn't mean object-oriented, doesn't mean generic, doesn't mean template, doesn't mean concept. It means whatever. It also means functional programming. And if you apply functional programming, all the concepts which we described before are equivalent to a function. Because what is single responsibility principle in functional programming equivalent? A function. What is dependency inversion? It's still a function. Like everything is a function, right? So it doesn't mean we cannot apply it. It doesn't mean the rules don't stand, because Law of Demeter, for example, is really easy to apply with the functions because we just have one call always, right? It's harder to screw up. So functional programming is a good idea sometimes to follow, although it has its own drawbacks, which we won't discuss here. But that's a really good talk. If you're not really into functional programming, I really encourage you to watch it. It's really good. And the last thing, Andre is at this conference, so you can talk to him about it. Policy design or design introspection is something which comes from D language mainly, and the policy design from C++. The idea is basically that we can apply templates and concepts with the specific of the requirements and inside the code, and inject the policies as well. So the policy design is basically about injecting types which satisfy specific concepts. And design by introspection means that we can verify during the instantiation whether the given object satisfies our requirements. If it does, we do one thing. If it doesn't, we do the other thing. So a lesson here from the all this talking I've done for a few minutes is the fact that we should consider using the proper abstraction for our project, right? We should use templates or concepts if you know dependencies at compile time. However, we have to be aware that they're contagious and they will spread around. Type erasure is a fancy thing to use instead of the inheritance. We have the runtime dependency here, meaning that we don't know it at compile time. For example, we read it from JSON or XML or whatever. We just don't know it. And inheritance, I would argue that we should never apply it. But that's just personal opinion. I think it's coupling us to the interfaces and has performance drawbacks and is hard to change. And and this talk is all about etc. And it's harder to change than the other ones. So I would encourage it. So let's quickly take a look into the concepts application for our simple examples we have. So we have a speaker. Speaker can talk. And that's the requirement for it. I hope that most of you can apply concepts already in the code you are using. And that's not too scary to look at, because the syntax is maybe not ideal, the requires. So we have this regular speaker, which takes the strong type first name and last name. Notice here that there is no inheritance. We don't inheritance from iSpeaker, which implements the talk. So in that case, we're not coupled, easier to change, etc. applies. And then we can propagate it to our CppCon talk. I notice here that we passed references, and that gives us the ability to easily change it in the tests, meaning that we'll create a fake speaker in the test and just propagate it, and then the instance will hold all the expectations. But as I pointed out, we apply DI here with the speaker and the attendees and their concepts. So if you propagate something which is not suitable, doesn't satisfy the requirements, it will bail out. We also introduced the wiring, which we won't talk about much right now. But that's the factory. That's the main part of I'm creating all the objects. That's not the business logic. Business logic is where we want to spend time. This part might be totally done by DI or DI framework or factory framework or whatever. But that's something which we have to do. And that's where we want to not spend time on. So the wiring is something which separates the creation logic from the business logic, as I pointed out, meaning that in our business logic, we don't have any new, make, unique, or anything like that. That's all of that. It's moved to the creation logic. And the composition route is something where we, like in the main function, we wired everything together. And that's one place where for the whole application where we do that. And that's a really good approach, because then we can see where everything starts and everything is created. We don't have factory here, and then it's the business logic and then this factory inside creating things. No, everything is in the one place. So what about this dependency inversion principle? Is it flexible? I would argue it is. Is it scalable? It's more scalable than it was. Is it testable? Yes, we can inject fakes, so it's much better. But what about this testing? Now, I promised that that's the solution for everything, and I think it is. Let's take a look into the behavior-driven development and how we test this concept example. So as I pointed out, it's testable, so we can create the speaker, attendees, and the talk very easily by having fakes. And then we expect the calls for the talk and the ask. And notice here, so that's BDD given one then. That's not really important to think about. But the main part is we have the fake speaker and fake attendees, which we inject these objects, not names, not anything else, into the talk. We execute the talk run and expect that the speaker will talk and the attendees will ask the questions afterwards. So BDD gives us NTDD, loosely coupled code, easy to change code because drives, etc. Well, and it's testable, right? It would be hard to apply BDD without being testable or TDD. So yeah, consider test driving your code, I would argue. And BDD is, and the distinction between them is the fact that BDD uses automated examples to guide us towards building the right thing, and TDD uses unit testing to guide us towards building it right. I think that's the really important distinction between the BDD, and TDD, which we have to keep in mind. So we're running short on time, so I'll just summarize. So good practices are good practices for a reason. It's not that myself or anyone else come and talk about we should apply them. There's a lot of research, a lot of smart people did it, apply them, and it just works. In the long term, it's always good to do that. Solid is always better than, stupid. So applied solid principles is always better. And Law of Demeter. Law of Demeter promotes loosely coupled code, as we've seen. Less dots, it's better. Don't do arrows. Makes testing easier because we don't have to fake multiple dots objects. We just fake the one. TDD, BDD, single responsibility, dependency injection, all of them are way to go. And DI can be easily misused and doesn't require library on a framework. So yeah, let's only talk to our immediate friends. No. So with that, I guess we have 1 minute. So thank you very much. And if there are any questions, is that taken right now or afterwards? Afterwards. OK. Thank you very much.